All right, so guys, section 1.3, we're going to be talking an awful lot here initially about linear equations and two variables. And admittedly, I probably went a little too far or talked a little too much last period about linear equations. I think that we're going to be pretty confident with linear equations. We're pretty good with those. But it's just like the distance and midpoint formulas that we were doing yesterday, that just because you've seen it before doesn't mean we should just skip over it and just, assuming that everybody knows everything. Nah, that's a dangerous game to just assume that everybody remembers every single detail of math that you've learned in previous years. That's not very fair. And plus, if we're attempting to be as prepared as possible in this class, but also on the ACT that's coming up, knowing and understanding linear equations is a great place for us to really start here. So, like I said, we're going to definitely get through 1.3 today, and the hope was to get through 1.4. Like I said, we got almost through 1.4, so we'll see how sixth period goes here. But initially, we're going to talk about linear equations and two variables. Get that out of the way. This got cut off a little bit, I'm noticing. Sorry about that. But our goal is we want to be able to write linear equations in two variables. We want to use slope to graph linear equations in two variables. Then we want to graph lines given a linear equation. So again, graphing, using the graph, using the equation, working algebraically, working graphically, just really intermixing all of those concepts. So initially, when we're talking about linear equations, we're talking about linear equations, probably aren't going to take a whole lot of time before we start looking at y equals mx plus b. Does anybody remember, what do we call y equals mx plus b? What form is that? Slope intercept. A lot of people were talking at the same time and nobody talking loudly, so I think I was here. But slope intercept form is what this is called. So guys, again, I'll be the one to break the news to you if you haven't figured this out already, but mathematicians are not creative. These math professors that write textbooks, they're not creative. Why do we call it slope intercept form? Well, because you need the slope and because you need the y-intercept. So we call it slope intercept form. Here in a couple slides, we're going to be talking about point slope form. Well, that's when you have a point and you have the slope, so they call it point slope form. Again, nobody's creative or thinking outside of the box. It's just very direct. Here's what you have, so we call it this, right? So again, the slope intercept form, y equals mx plus b, it's maybe the sixth year now that you've been working with this form. This is definitely the most common form. It's not the only form. I'm talking today about slope intercept and point slope form. We also have standard form. That's another big one that's out there. It doesn't really fit with the graphing and stuff that we're going to be getting into. The standard form problems that we see, we're going to immediately put them into a different form. But slope intercept form, m is representing slope. Remember in this class when we talk about slope, again, we want to start to, convince our brains that we hear slope, we think rate of change. Or we hear rate of change, we think slope. Again, it's interchangeable in terms of phrasing. But again, y equals m slope times x plus b is the y-intercept. That is the constant. Y-intercept, remember, that is just literally where the line is crossing the y-axis. Okay? A lot of different formats and ways that these lines can look. Again, this first line over here on the left has a positive slope. So we would say that this function is increasing. It's growing. It's got a positive slope. Here we have a constant function. Again, we'll talk more about the increasing, decreasing, and constant tomorrow. But again, this constant function is a horizontal line. It's consistently staying that same value. And then this last one over here, we have a negative slope, which is falling or decreasing. But these lines, we read lines the same way you read words and sentences. You go from left to right. That's how we read them. So again, this is positive slope because it's increasing. It's going up as we read from left to right. Constant, it's staying the same. Negative slope, it's decreasing. It's falling as we go from left to right. So this first line, y equals 2x plus 1. Again, the 1 is representing that we're crossing the y-axis at 1. The 2, my slope, again, a lot of times, and again, slope is the rate of change. It's a little bit different than a lot of the other mathematical things that we come across. Oftentimes we prefer that slope is in fraction form. Again, when it's not, sometimes we we still put it in fraction form. So as we're looking at the slope here is 2. Some of us, I'll zoom in so we can see that a little bit more clearly. If we're looking at the slope as 2, some of us may in our minds say, yeah, well, the slope is 2 over 1. That's going to help us to see and locate, all right, we'll rise over run. I'm going up to right 1, up to right 1. As we talked about the constant, the horizontal line, here we are crossing the y-axis at 2. That's why we call this line y equals 2, not to be confused with x equals. If it were x equals 2, that would be a vertical line because you'd be crossing through the x-axis. Fully get it and understand how and why people mix those up. The x-axis is horizontal, so shouldn't x equals 2 be horizontal? It actually doesn't work that way. Like I kind of verbalized it this way. When you see a line y equals 2 given, understand they're telling you to go through the y-axis at the point 2. That's the y-intercept at 2. I'm going through a vertical line would not go through the y-axis. The vertical line would be mapped over top of the y-axis. Does that make, do we see the difference there between those? All right. Chances are, as pre-calculus students, this is something that you figured out already. Just trying to remind you some of these little details that are going to help us to be successful. Last one over on the right, which I've really cut myself off here. I don't know how that all happened. But on the right, we've got y equals negative x plus 2. The y-intercept is at 2. My slope is negative 1, so I'm going down 1, right 1 to fall in that ratio. Guys, do we have any questions about the graphs of these linear equations? Have you seen it before? Absolutely. Multiple years in a row. But this is not something this isn't the year that we can afford to just forget about it, right? So again, we want to make certain that we understand and continue to understand what this is all about. So a little bit more on slope-intercept form. Excuse me. Again, we've got it up here, y equals mx plus b. But given an equation of a non-vertical line, you can find its slope by writing the equation in its slope-intercept form. And the translation there is that if you have any equation, whatever the form it may be, we can get it into slope-intercept form. And for graphing purposes, that helps. That's really nice. But I guess what we're trying to say is that not all equations are going to just be given to you in slope-intercept form, as you know. Also want to point out, very specifically, they point out that, hey, this works for non-vertical lines. What's the problem with vertical lines? Why couldn't I write a vertical lines equation in slope-intercept form? What do you think, Tail? Yeah, it's going to be really difficult because the two things that you need to write it, the equation in slope-intercept form, you must know the slope, you must know the intercept. So if Teo is absolutely right when he says that the slope is undefined, another way we could say that is that the slope does not exist. Like, it's not real, it's not there. Like, it's not 0. 0 is the slope of a horizontal line. A vertical line, there literally is no slope. Okay, it goes right back to, we know that slope is rise over run. So if you have a vertical line, yeah, it's going up, say a number. Again, it's going up 7, but over 0. So the ratio is 7 over 0. Hopefully, even just my saying that out loud actually makes you uncomfortable. We can't divide by 0. You can't have 0 in the denominator of a fraction. That's when things really go, it goes haywire, so to speak, right? So again, we cannot, under any circumstances, have 0 in the denominator. That's why, as Teo was mentioning, slope does not exist. It's undefined. Therefore, how could we even symbolize that? How could we start to write that? Y equals undefined times x. Like that, it doesn't make sense. It's not a thing. So what we would have to do is really abandon the y equals mx plus b idea. And fortunately, we just go with the fact that if it's a vertical line, maybe the x-intercept is 5. All right, vertical line through 5 crosses through the x-axis at 5. We call that line x equals 5, right? Again, not telling you anything that you don't already know, just trying to remind you of some of this stuff. Okay. Also, if you are not given an equation, you can still find the slope of the line. We could look at the picture and we can count boxes. We could do it that way. But also we continuously have in our back pocket the fact that slope is going to be the change in y over the change in x. It's the rate of change. That's what slope is. Or if we have coordinates, remember y2 minus y1 over x2 minus x1 as we used yesterday. All right. First example, we want to find the slope-intercept form of the equation of the line that passes through the coordinates 2, 1, and negative 1, negative 8. So I believe that we would be using this formula. That's going to be where we're at in an attempt to find M, and eventually we need to find B. So again, our game plan, if you will, is to write this out, y equals mx plus b. In order to satisfy, we're not trying to solve for x and y. That's not the goal. The goal is that we need m and we need b. So if I'm giving these two coordinates, the first coordinate we could vary here, but I'm going to call it x1, y1, x2, y2. Do we agree that we could calculate the slope by taking y2, negative 8, minus y1, which is 1, over x2 minus x1, so negative 1 minus 2. And fairly quickly, we could start to make some progress. Negative 8 minus 1 is negative 9, over negative 1 minus 2 is negative 3. So hopefully we're solving the mystery here that the slope is going to be 3. If you would prefer to rewrite that as not just 3, but 3 over 1, great, go nuts. I would say for graphing purposes that may be helpful, but for the equation, I think writing it as m equals 3 is probably our better option, okay? Not to say that it would be incorrect if you did it the other way, but hey, we're off to a good start. We're halfway home, we have m, now we just need to figure out b. So, what we could do, if we really wanted to weigh our options, we could go up there, we could grab some graph paper, and we could plot a point at 2, 1, plot a point at negative 1, 8. We could draw the line in between. We already know that the slope is going to be 3, and we can just keep our fingers crossed. Maybe we use a straight edge to really, really, really do it right, but maybe we are going to draw it perfectly to where we could see the y-intercept, and then we know that b is some value. We could do it that way. Could we algebraically figure out b, though? Yeah. Okay. So jumping back over here, we're filling in y equals mx plus b, and we've already established that m equals 3. So we're now able to say that y equals 3x plus b. So the way it sits at this moment, I have to figure out b. I have to solve for or calculate b. I have too many variables. We can solve any equation, no matter how complicated it is, as long as we have one variable. We can solve for it. By my count, we have 3 variables going at this stage. But luckily, we have substitutors, right? We have values that we can plug in place for x and y. In fact, we have 2 options. We're given 2 coordinates, so we could use the coordinate 2, 1, because when x equals 2, we know that y equals 1, or we could use the other coordinate, negative 1, negative 8, because when x equals negative 1, y equals negative 8. Now, hopefully you just believe me when I tell you or remind you, we could use either one of these points. Either one of these points, you're going to get the exact same answer, exact same value for b. But do we have a preference as to which one we would use? I'm hopeful that we're all on the same page without really saying it out loud. I think that using positive 2, positive 1 is going to make our lives at least seem a little bit easier. But if you like to make things harder on yourself and you use negative 1, negative 8, promise you, you're going to get the right answer, okay? So we're at this stage establishing that we're going to let x equal 2. We're going to let y equal 1, pulling that directly out of this coordinate. And as we plug in 1 in place for y, times m is 3, times x is 2, plus b. So now when we do the math, we solve for b. 3 times 2 is 6, plus b. When I subtract the 6 over, now after all this work, we have that b is equal to negative 5. So at the start of this problem, clear over here, we said that we needed m and we needed b. We have those things. So now I could fill in y equals mx plus b, so y equals 3x plus b is negative 5. All right, guys, so does that process seem familiar? So this is something that you would have learned how to do in Algebra 1. You would have used it in geometry, used it in Algebra 2, and here we are. We're using this again in pre-calculus. And guess what? You're going to do this in calculus also. The good news is you've seen this. It's relatively familiar. Also, I don't know if this is good news or not, but you're going to do this on the ACT. I mean, I feel very confident in saying, even as a guy that does not write for the ACT, I've looked at and studied enough of those, you're going to see this on the ACT or some version of this type of question. All right? We want to go ahead and sketch a few of these graphs. We want to practice this really quickly. looks like we've got A over here. We'll do that one first. So y equals 3x plus 2. Could get a little bit of help. What is M? 3. What is B? All right, so as we go to graph this, y-intercept is 2. That's where I start. How do I get to the second point? My y-intercept is at 2, so I have a point there. How do I get to the next point? Yeah, that's where the slope comes in, right? So 3 or 3 over 1, I'm going to literally go up 3, right 1. We could do the opposite. What's the opposite of up 3, right 1? Down 3, left 1. And we could keep that pattern going, looking something like this. All right. Next up, this is, I don't know if it's really fair for me to call it a weird one, but y equals -3. We're going to go through the y-axis at -3, so we know we're going to hit that point right there. What kind of line are we about to create, horizontal or vertical? Horizontal line, good. So y equals -3, there it is. All right, next up, we have a little bit of a problem. I wouldn't say it's a serious problem, but we do have a little bit of a problem. On A, we were able to just glance at it and say, oh yeah, the slope is this and the y-intercept is that. I bet that we could get there, but we have to think about it, right? Are we currently in slope-intercept form? Not yet, but not much has, in this particular equation, has to be done to get into slope-intercept form. In slope-intercept form, we just have to isolate the y. We have to get y all by itself. So the path is to subtract 4x over. Now we could say that y, isolated by itself, is equal to -4x plus 5. Now again, this is not my answer, but now we're in slope-intercept form, and we could start to answer those same questions. What is my slope, please? What's M? -4, and B is 5. So we're going to start, y-intercept is at 5. My slope is -4, or -4 over 1. I'm going to count down 4, right 1, down 4, right 1, and we have this line. Looking something like that. All right, guys, how do we feel about graphing lines? We haven't forgotten this over the summer. We probably forgot a lot, but we didn't forget how to graph lines. Good news, good news. All right, point slope form. For whatever reason, a lot of students, it's probably just because the look of the equation, point slope form doesn't seem to be nearly as popular as slope intercept form. To be honest with you, it's not as applicable, or it's not as widely used, is probably a better way for me to say that. But there are plenty of times in math that we don't really need the y-intercept. We don't need it. Who cares where the y-intercept is? As long as you're given a point, if you know what the slope is, could I just give you some random point and tell you the slope, and could you draw the line? Yeah, there isn't anything out there that says you have to start at the y-intercept, no matter what. You must. If I told you, all right, go to the point 3, -7, put a point there, and then your slope is 2/3. Could you draw at absolutely. You could draw that line perfectly and be very effective with that, okay? So there are times and places to where you need the y-intercept. If so, slope-intercept form is your option. There are going to be times that you don't need the y-intercept, and we'll help you to decipher when and how those are going to look. But the point slope form, we've got y minus y1 is equal to m times x minus x1. Remember that you're given the slope, m, and you're given a point, x1, y1. Everything, it's just substitute in place and clean up from there is what that's going to look like. All right? So this first example, or second example, excuse me, it says that we want to find the slope-intercept form and the point-slope form. So that's what we're going to do first. We're going to find the point-slope form of the equation of the line that has a slope of 3 and it passes through the point 1, -2. So if the slope is 3, that tells us that m equals 3. If it goes through the point, now we know x1, y1. So we know that x1 equals 1, y1 equals 2. So as we're building the point slope form, so the point slope form is going to look a little something like this. Y minus, what's y1? -2. And that's equal to, what's my slope, please? 3 times x minus, and what's x1, please? 1. Last thing we need to do is clean this up. And when I say clean it up, I mean that we want to get rid of the double signs. We don't want to leave that written as y minus negative 2. We would clean that up to say y plus 2 equals 3 times the quantity x minus 1. Now, oftentimes students will say, yeah, but don't I have to distribute the 3? If we start doing that, it's going to start to look like slope-intercept form fairly quickly, which just so happens is the next thing we want to do. So we have the point-slope form. If I wanted to turn this into slope-intercept form, all we have to do, remember, is isolate the y. So if we're looking at y plus 2 equals, when I distribute, we'd call that 3x minus 3. So if I were to simply subtract the 2 over, we have y equals 3x minus 5, and there is our slope-intercept form. Okay? Guys, how do we feel about some of these linear equations? Pretty good or pretty great? Only give options that I like, right? So, okay. All right, so next up here, we've got a couple of these word problems, which at times can be kind of tricky, but oftentimes they're, if we just really stop and kind of take a look, take stock in what it is that we are given and what we're trying to find, we can generally get there. So this example says the college buys exercise equipment worth $12,000 for their fitness center. The equipment has a useful life of 8 years. So what that means is that we're buying it now, and we know that in 8 years we gotta replace it. We gotta make a move. The salvage value after 8 years is $2,000. So I can still recoup two grand when I get rid of these in 8 years, right? We want to write a linear equation that describes the book value of the equipment each year. All right, so don't take this the wrong way, but I'm hopeful that we don't have to do this every time. But as we're first building this out, perhaps this is going to help a little bit. But if we were to turn in, or if we were to create ordered pairs with this. So like right now, if I were to buy the equipment, do we agree that right now, if I'm buying the equipment, that 0 time has passed? If I'm making the purchase today, how long have you owned these? If I'm making the purchase like as we speak, I've owned them for 0 minutes or 0 days or 0 months. Okay, we're in agreement there. All right, so 0 time translates to how much is the cost? $12,000. So I think that for argument's sake, let's count time as in years. So after 0 years, it's worth $12,000. We're good with that? So after 8 years, what's the worth? How much could I get out of it after 8 years? $2,000. So if we start thinking about these as just big ordered pairs, do we know how to build an equation out of this? Yeah. Could we think about y equals mx plus b? Guys, it doesn't matter if you're writing an equation or if you're trying to draw the graph. If you're in slope-intercept form, the two things you need are the slope and the intercept. Well, do we already have the intercept if we just look closely? Isn't every y-intercept going to be 0, comma, whatever the y-intercept is? So does that start to look a little bit more like the y-intercept? Does everybody see how we got there? That b is equal to 12,000. Okay, now m, the slope, I'm gonna have to work for it a little bit. So we have a formula for that, luckily. So if we were to go, let's go y2 minus y1 over x2 minus x1, looking something like this. So now we're looking at 2,000, minus 12,000. So we're going to get negative 10,000 over 8. So what is that going to be? Negative 1250, is that correct? For my slope. So what does that tell me? If our rate of change is negative $1,250, what does that mean? Yeah, every year it loses $1,250 of value. Does that make sense? So if that's M and that's B, do we agree that I could use that information to write y equals negative 1,250x plus B is 12,000? Like that? How are we doing here, guys? Hanging in there? Is it making sense? Feeling pretty good? Feeling pretty great? Okay. All right. This next one's a little weird. I'm going to try to go a little faster through this one, but it's very, very similar. I'm really tempted to skip over, but there's just one little piece here that's different that I do think there's going to be value in. So, next example, it says that the population of Texas was about 29.1 million in 2020 and 30.5 million in 2023. Use this information to write a linear equation that gives the population in millions in terms of the year. Predict the population of Texas in 2030. Okay, so if we started building this out the same way as we did the previous, that again we could create some coordinates and things like that, but I don't know. If we wrote it out, that'd be great. If not, that'd be great too. So my slope, if I were to look at rate of change, I should call it, sorry, I'm going from 29.1 million, and 3 years later I'm at 30.5 million. So do we agree that I could find that difference by taking the 30.5 minus the 29.1? And this is happening from 2020 to 2023. So do we agree with the slope formula that I'm very sloppily writing up there? Is that making sense where this is coming from? So now if I actually do the subtraction, I'm sure that I have some notes written down somewhere. I keep losing my place here. 30.5 minus 29.1, I don't know, I'll find it eventually in my notes, but that's going to be 1.4. 2023 minus 2000 is going to be 4. Again, we could go fraction form. There's a lot of different options. I found my notes here. So that's 0.46 repeating, which happens to be 7/15. How are we feeling about obtaining the slope? We feeling pretty good about that? All right, now, things could get a little strange, a little wonky, depending on understanding our model. Now, I know that we are going to study exponential growth and decay and logistic growth models in the future, and I feel like we're kind of we're like tiptoeing into a logistic growth model, which I realize I don't think you know much about yet. But for this particular model, we've got to understand that they didn't talk about any of the population or anything before 2020. So for our purposes, it's like everything started in the year 2020 in accordance to this problem. Does that make sense? So if that's the case, could we agree or act as if my y-intercept is that 29.1 because that was the population when we started? Does that make sense, how we're approaching that? So if that's the case, now we could build out that y equals 7/15 x plus that 29.1 million. So to make things, again, if it didn't get weird yet, now to make things extra weird, we're figuring out what's happening in the year 2030. Well, all that we really need to do is figure out what does x equal in the year 2030. So remember, we said that for our model that we're building, this guy right here, it's as if year 0 was 2020. How much later is 2030? How many years later? Is it 10 years? So all that we're going to do is we're going to let x equal 10, aren't we? So in our model, we're going to write that y equals 7/15 x plus 29.1, and we are going to allow x to equal 10. What if we changed our mind and said, hold on, I'm sorry, it's a typo. That's supposed to be 2031. Then what would we let x equal? 11. It's just how much beyond 2020 are we talking here, right? So if this is the case, if we were to type this in, it's all calculator work at this stage. We're going to, I keep losing my spot, are we going to obtain 33, man, that is sloppy, 33.767 million? Should write the million as well. All right, in the AP world, when you are in decimal form, you'll always round to 3 decimal places, is what I understand. Okay? All right, guys, how do we feel about this so far? So far, so good? All right. We're not getting through 1.4 today. I know that, but we're gonna get what we can here. I'm very confused as to why everything is shifted over this way, and I can't seem to get there. But again, functions. We've talked a lot about functions in previous classes. But the goals that we have, we want to determine whether relations between two variables are functions. We want to use function notation to evaluate functions. We want to find the domains, and then eventually the ranges, but specifically the domains of the functions. And then we want to use functions to model and solve some of these real-life problems. All right, so what is a function? The good news, the great news is you've been working with functions for years. Also, in Algebra 2, I think that you started to define, hey, this is a function, this is not a function, those types of things. But the simplest way to address this is to say that a function is going to be a relation that maps each input value, so like your x's, your inputs, to exactly one output value, your y. So what this means is that what I put in place for x, I get something back out for y, and whatever I put in place for x, I'm going to consistently get the same unique value back out for y. So, Renzo, what numbers should we use? Anything you want. 7. All right, so if we were to use 7, and we let x equal 7, that just means that we're going to substitute 7 in place for x. If we know that x equals 7, 2 times 7, 14 plus 1, y is going to equal 15, correct? Okay, so what if we did the same thing? What if I asked the same exact question, wrote the same equation, Renzo gave the same x equals 7. If we did the same exact thing tomorrow, are we going to plug 7 in for x and still get 15 out for y tomorrow? And the next day? And the next day? All right, what if... okay, Katerina, what if we had you reach out to some friends back in Italy and you did the exact same thing? Are they going to get that y equals 15 if we put a 7 in for x there? Absolutely. Okay? So the point that I'm trying to make, the stupid point I'm trying to make, mind you, is that it doesn't matter when or where or how many times. If we put 7 in for x, you're going to get 15 back out for y every single time. It's not going to change. If it does change, it's not a function. But since this is consistently going to give the exact same output, this is a function. This is a linear function. We would be in real trouble if we said, yeah, we put a 7 in place for x, and we usually get 15. Sometimes when we put a 7 in for x, you get 28. You know, it's just kind of weird that way sometimes. If that were to happen, no problem. It's just not a function, okay? Like, for instance, we've seen that before also. If you saw something like this, and we let x equal 25. All right, what's the square root of 25? 5. Except for when it's negative 5, right? So sometimes we get 5, sometimes we get negative 5 back out. So that's why this guy here would not be a function, would not follow those same patterns. Okay, so there are a lot of different ways that we could build this and express this and, you know, essentially talk about this. The time and the temperature, this is one of the models that I feel like is easier to understand. Again, a lot of us, we look at, I don't know, I do anyway, look at the weather apps on my phone. All right, what's the temperature going to be today? What, you know, at this time, what's it going to be? Is it possible that at various times of the day that it's the same temperature outside? Like, could it be 83 degrees at noon and at 5 o'clock? Sure, that can happen. What can't happen is at noon, it's 83 degrees and 64 degrees and 100 degrees all in the same location. That's what can't happen. All right? Maria. Yeah, thanks. All right, so we can address functions in multiple ways. We can get there. So the one thing that I do want to ask, again, we're going to circle back to some of this stuff tomorrow, but function notation. Notations is just fancy words for how you write stuff. If you were to see this, it's the last thing that I thought that we might get to today, but if you were to see that f of x is equal to 1 minus x squared, and you're asked to evaluate f of negative 1, do we understand that that's just fancy substitution? Everywhere that I see an x, what am I going to put? Negative 1. And we could get there that way, correct? Does this look familiar? The way that I understand it, this is something that you would have seen last year in Algebra 2, but it's definitely something that we're going to take to the next level here. Piecewise functions, that was the stuff that I knew, or I did not think that we would get to. I thought we might get through a couple more of these examples, but that's a my problem, not a your problem type thing. So let me stop this.